thought we'd do today to get started is, last time we did a little example. And again, this is all within the context of trying to create an interpolating polynomial. And what that requires is, well, to do that, you're going to establish a system of linear equations, and to solve that system of linear equations, the technique we'll be using is Gaussian elimination. So it's just another context problem of the use of use of Gaussian elimination to solve system of linear equations, different than the one we started with, which was partial fraction decomposition. All right. So for a simpler example that everybody can do, let's say our data are just those 4 data points. Okay, so here's 1, 2, 3, 4, 1, 2, 3, 4. So we got this point here. We got that point over there. And we have this point over here. And then 4 to this point. So that's our data. So what degree polynomial will we be trying to generate that will go through all 4 of those data points?
Third.
Sorry?
Third degree? Right?
Degree 3?
Yeah.
Yeah. Because it's always n minus 1. So here is equal to 4. So the polynomial is going to be of degree n minus 1, which is equal to 3. So the polynomial we're looking for is, we call it p of x, is a sub 3 x cubed plus a sub 2 x squared plus a sub 1 x plus a naught. So that's our polynomial that we're trying to find. And to do that, we need to figure out what those coefficients are. So since we have those 4 points, we can generate our system of linear equations based on the relationship of a function. So if we have x and it's going into this function p, then p of x comes out. So for some value of x, there's this mapping of x to p of x. Right? That is what it means to be a function, right? For a unique input, it produces a unique output. Or better yet, for a given input, it produces a unique input. Since it's a function, any input cannot produce multiple outputs. But 2 different input values can produce the same output. That's fine. Okay. So from this, then, we can generate our system of linear equations by saying a3 times 1 cubed plus a sub 2, 1 squared, plus a sub 1 times 1 plus a naught is equal to 1. A sub 3, 2 squared, plus a sub 2, 2 squared, plus a sub 1, 2, plus a naught is equal to 4. A sub 3, 3 squared, plus a sub 3, 3 squared. Sorry, these should be cubed here. 2, 3 squared, a sub 1, 3, plus a naught is equal to 3. And finally, a sub 3, 4 cubed, plus a sub 2, 4 squared, plus a sub 1, 4, plus a sub 0 is equal to 2. So that's our system of linear equations. Is there anybody here that does not understand how those equations came about?
I just have a quick question about like the a sub. Is that just to denote that it's a different variable? Like the a sub 3, a sub 2?
Well, they're the coefficients. So remember the general definition of a polynomial is a sub n x to the n plus a sub n minus 1 x to the n minus 1 plus a sub 2 x squared plus a sub 1 x plus a naught. So a just represents the coefficient. The subscript represents which power of x it's a coefficient of. So just keep in that convention, this a sub 3 is the coefficient in front of x cubed. They are not variables. Once we find the polynomial, they're constant. But right now, they are variables in the sense that that's what we're trying to solve for. Does that make sense?
I don't know, how do you know that n equal 4, or you just do that?
No. 1, 2, 3, 4. N is the number of data points. So we only have 4 data points, therefore n is equal to 4. So there's a unique degree 3 polynomial that goes through all those. Are there any other questions about how those equations came to be? Well, if you understand how those equations came to be, then from the next step is to find those coefficients. So the system to perform is A x is equal to B, where x is equal to the unknowns, a sub 3, a sub 2, a sub 1, and to find those, we're going to use the Gaussian elimination method to do that. So this is relatively easy to solve, so why don't you take a couple of minutes and see who can come up with those coefficients.